Hello, everybody, and welcome to this presentation of our demo paper entitled CACSE, Context-Aware Clustering of Stellar Evolution. My name is Goce Trajcevski, and this is a joint work between several teams and multiple people are listed here. Juan and Prabin are graduate students, whereas Adam, Joel, Willis, Becker, Philip, and Ethan are undergraduates at Iowa State. Aaron, Jeff, Scott, Ying, Huanga, they're part of the Northwestern team in this research, and Nam, Jaime, Konstantinos, Emmanouil, Simone, Devina, and Tassos, they're from University of Geneva in Versoix, Switzerland. The last two teams are the ones that are working on astrophysics part of this. So to introduce the problem, to motivate this work, this is about stellar evolution. So what is a stellar evolution? One can perceive it as, complex trajectories which are quote-unquote moving in a non-Euclidean space. Once the star is formed from a nebula, it goes typically over a few distinct stages, depending whether it's a low mass or high mass. It will go through variations in the main sequence, but past that main sequence, the star becomes a red giant or a red supergiant, and goes into either planetary nebula and ending in the white dwarf, or a supernova, which, it can end up in a neutron star or black hole. The second image basically shows you the stages of the so-called main sequence, and these internal processes within the main sequence depend on helium, nitrogen, carbon concentrations, the radii, and so on, multiple parameters. So it's a very complex system that we're talking about. Now, these problems are investigated by theoretical astrophysicists, and they're concerned with stellar dynamics and evolution, galaxy formation, structure of the matter, and so on, relying on multiple branches of physics, from classical mechanics and through thermodynamics, all the way to quantum and particle mechanics. Complementary to this, there is the observational astrophysics, which is focused on recording and interpreting data obtained through optical, infrared, X-ray based ground and space-based telescope. Now, there are certain issues in this picture, as you may have guessed so far. For the record, in existence, there are large repositories of observation data, such as Sloan Digital Sky Survey, Gaia. We provide a link for these in the paper for the one who's interested. And some of them even provide SQL interfaces. Basically, the data is tabulated and you can query it. Now, complementary to this, the issue is that, typically theoretical models tend to use equations or system of differential equations. However, they're limited to expressing dependencies of a few parameters. For the rest of the parameters, they put boundaries on interval of validities of those differential equations. Now, in addition to these issues, the complementary part, the observational astrophysics, well, to begin with, it has a limited reachability in a semi-spatial sense, right? We only get data with a delay, significant delay of light years of travel, and within a limited portion of the sky. Moreover, observational physics can generate quantitative data within only the last few centuries, whereas we're talking billions of years of evolution of the stellar. Now, oftentimes, what physicists do when they want to examine the models to justify them, they use the limited observational data and they resort to simulations. One of the most popular simulators in the astrophysics community is the MESA, Models for Experiments in Stellar Astrophysics. And by way of MESA, one can generate much larger data sets than the one that observational astrophysics can actually record. Now, quite often, the output of those simulations may be tabulated, maybe even SQL queryable. The problem, though, is that the analytics tools for such data are still at their infancy. At the core of the problem is that the data pertains to a large number of time instants Now, here somebody may be tempted to say, well, why don't we use multivariate time series? True, that's a viable option. The problem is, though, in addition to the volume of the data, the number of attributes, all of which are of heterogeneous physical nature, is also large. Typically, the data sets are tens of gigabytes coming out of a simulation. But as I mentioned in the previous slide, one of the issues is that the number of attributes can range from 40-something to sometimes a little bit over 100. What I'm about to present is part of the Poseidon project, the astrophysics project, that is run under this joint collaboration between Northwestern University of Geneva and Iowa State University. And as part of this project, we have developed our own web-based SQL interface, a snapshot of which I'm showing here, where the users can select the data set, check the attributes that they want to query for certain ranges of their values. Actually, the interface is much richer. We can remember the queries that a particular user asked. We can have readily stored queries. We also have templates that the users can edit. However, that's a subject of another work. What we're focused upon here is motivated by the following observation. The data generated from different simulations within the dataset not only has a big number of heterogeneous attributes, but there is also a mismatch between the recorded time instance. That's a consequence of the way the astrophysics simulations are designed. So the commonly used time series approaches, they're not straightforwardly applicable. I'm not talking only about the mismatch. One can think of immediately of dynamic time warping and variants of it. What I'm talking here also is about simply the dimensionality curse. Yeah? Now, specifically what motivated this work is the following. An astrophysicist may be interested only in a few attributes, and moreover, what is the role of those attributes if I want to generate clusters, investigate clusters of stars? And for those few attributes, the astrophysicist may say, can I see which one is actually more important? Can I put a different weight on that attributes and see how it affects the clustering? So towards that end, from numerical perspective, to get rid of the heterogeneity for each attribute or dimension, what we did is we detected the minimum and maximum values, and we calculated relativized values within that range from the actual generated outputs. So for example, if we have a mass at a given time instant t, we have a relativized mass of a star I by dividing that value with the difference of the max and min values of the overall simulation output. As far as the temporal values are concerned, what we do is we look at the entire data set, we take the union of all the factual time instants for each quote-unquote trajectory of the stellar evolution, and then if the value of a given time instant is not explicitly available, we use linear interpolation for each parameter or for each attribute to insert the value of the attribute at a time instant. Now, when it comes to clustering, we use the typical Euclidean distance functions over relativized values. At present, the CACSE system has two methods that the user can choose from, the k-means and the dbScan. Lastly, in order to enable astrophysicists to push a little bit heavier on some attributes of interest, what we do is we modify the distance function to cater to weights. For as long as the sum of the weights is 1 or 100% in percentage, what it means is that 3, 4, 5 of those attributes can be given actual weight. The rest will be sent to 0, so they will not be, impactful in the overall comparison. Briefly about system architecture, there are 3 main modules: the front end, the back end, and the middleware. As part of the back end, we have this data access layer, which is a PostgreSQL database. Those are the tables for which we have scripts that take the simulations output and put them in SQL tables. The middleware basically is what enables, first of all, communications between the database and the user interface. We relied on RESTful and Django frameworks, and for communication of the values, we use the JSON-style packages. To execute the clustering algorithm, we used Python libraries that are readily available. The web-based user interface, we used Angular framework to develop it. And at this point, I would like to bring to your attention that you're more than welcome to see the paper, because we provide a link to works related to the whole project that describe in detail the different design decisions. We actually also talk about testing methodologies that we did, from unit through interface and acceptance test, and so on. And of course, there is the code is publicly available. Just to wrap up this discussion with respect to the web-based user interface components, they enable the user to select the database. By the way, we will see this in action soon, the actual demo. Upon selection of a database, user can just say, these are the attributes that I'm interested in, to see their impact on the clustering, at which point he or she will be also offered the option to select different weights. Otherwise, the default is that every attribute of interest is equally weighted when calculating distance. As that, the user is asked to choose clustering algorithm and to select whether the observations should pertain to a specific time instant of the trajectory's evolution, within that database, or to a time interval. We're going to see this in a demo momentarily.
Welcome to the Stellar System Clustering Tool. Today we're going to be featuring a quick demo of the 2 functionalities of this application. 1, creating a new query, and then 2, visualizing that query. We start out here on our home page, where we see a list of previous queries that users submitted. If we click onto one query, we can see details about that query. And if wanted, the user can then view that query. So let's create our own by clicking on the New Query button. The first step is to choose your database. Our application has 2 databases available, Cosmic and Poseidon. Next, the user selects which attributes they want want to be clustered by the backend. Any combination of attributes will work. Next, we need to define weights for each attribute. The larger the weight, the more that attribute will be affected by clustering. And we want to make sure that the weights all add up to 100. There also is the option to allow empty inputs, and this would even out every attribute equally. The user also gets to define which clustering method they want to use. We have k-means and dbScan implemented. Each of these clustering algorithms has their own pros and cons, and the user can decide which one to use. Depending on which clustering algorithm you selected, different parameters will be needed. For example, for k-means, the user needs to select how many clusters they want to cluster by. Certain data processors will optimize the speed of the clustering, And then finally, users need to select a temporal range. This could be, so in evolving stellar data, we can either look at one time instance or a range of time instance. For example, we can do time instances 15 through 21. At the end of a query, the user hits this review and submit page where they can review the query information, and when they're ready, click submit. Here we're back to the home page and we see our query loading. Let's look at what visualizing a query response might look like. The default graph presented is a two-attribute visualization where we have two attributes graphed over time. The user also can pick between two more graph types, displaying one attribute over time on a 2D graph, or displaying all three attributes on a 3D graph, where time is a input value. Let's take a look at that. So here we have three axes representing three attributes, and at the bottom we can increment the time step to see how the data will change over time. There's also a feature to select which clusters are visible and not visible. This way a user can zoom in on a specific cluster. That is cluster visualization and the main functionality of our application. Yeah, that's it.
So, to summarize, we presented the CACSE, an interactive system for clustering astrophysics data pertaining to stellar evolution. The CACSE has this feature of offering the clustering type of analysis for multiple data sets. Most of them are obtained through simulations, and typically they're not only large in volume, but also contain quite a number of heterogeneous attributes. What we also allowed is, in the interest of catering to astrophysicists' need to focus on certain attributes of interest, we allowed to put different weights when calculating the distances in the respective clustering algorithms. So far, we only have two of them, but since it's open source implementation, we welcome people that would like to expand this work, and we are also planning to incorporate different clustering algorithms. And we offer the feature of visualization of the outcome of the clustering. Now, for the future work, as I mentioned, we are going to incorporate a few more variations of DB-scan in particular that we're working right now, of clustering methods. And we will use the existing literature that enables one to judge the quality of the outcomes of clustering. And then lastly, at present, we're working to cover the clustering issues when it comes to binary evolutions or binary stellar evolutions. The main difference with the work that we presented so far is that when it comes to binary systems, what happens is that two stars are kind of entangled with each other, and many interesting phenomena can happen. One of the stars can be a donor, the other one can be a creator of mass or other elements. And to wrap up this presentation, I just would like to mention that the work is funded by the Gordon and Betty Moore Foundation and the Swiss National Science Foundation professorship grants. Thank you very much for your time and attention. At this point, I'd be happy to answer any questions that you may have.